Right. So we're going to talk about machine translation specifically. This is going to be a lot more, I guess, practical than David's talk. So yeah, so what is the thing? I know that a lot of you mentioned that you're interested in machine translation. So let's see how let's do a historic overview of how things have been unfolding in machine translation. So basically, the whole kind of like idea started back in like right after the Second World War, you know, and the whole thing with the Cold War and everything, where they naturally, like as Warren Weaver said in 1947, like you could conceive of the problem of translation as a problem of cryptography, right? So you could say you would see an article written in Russian, but you would say, well, no, this was actually, you know, really written in English, but it has been encoded in some strange symbols. So what all we need to do is decode in the same way that people would decode like encrypted messages, okay? It just happens that this encryption is another language. And interestingly enough, in the past, like uncommon or like rare languages have been used for encryption. So I don't remember which war exactly, but like the US troops used to use, have used like Navajo native speakers to communicate between different, I don't know, like troops or whatever in a language that no one else would understand, right? So that's just very interesting. So the important thing is that machine translation, like that translation is something that humans do natively. And as a result, we produce very, very, very similar, like very, very different types of parallel data, like translated data. So I want you to see this example again in Maori, the New Zealand language, from a McDonald's, okay? And this is how you can order coffee, right? Kawe, I hope I'm pronouncing this correctly, in Maori. And the interesting thing that I would like you to do is see these 1, 2, 3, 4, 5, 6, 7 sentences, and you see how you can order like a flat white or a short black coffee or a long black coffee. So here's a question for you, right? How would you say, I will have, let's say, a short cappuccino? Like, feel free to just give it a try. Like, don't need to raise hands or something.
So I think it could be something like, I don't know if I'm pronouncing it correctly,
Right.
but it could be like, hey, cappuccino, poto mako.
Okay, I think that's correct. But how do you come to this conclusion?
So I sort of look for minimal pairs. So I'll have a short black and I'll have a long black. Well, if you compare these two, you can see conclusively that poto means short and roa means long.
Okay, does everybody see this? Cool. All right, and how would you say I will have? Like, I'll have.
Yeah, so for that, every sentence has hey and mako first at the end. And I'll have is also the only common phrase out of all of them.
Right. So
So you can,
yeah, so that's generally, you know, like the process if you wanted to do something like that, right? Of course, if you think about it, that's not the way that if you learned a new language, if you ever went to like, you know, a language school or anything, or to learn a new language, that's not the way that you would learn how to translate, right? No one would give you, okay, here's all of Wikipedia in English and here's translations in French. Now learn how to translate in French, okay? But the interesting thing is that by looking at these types of data, we can actually figure out what these differences are. And as you'll see later, we will do this. This is something that we can model computationally, okay? So I wanted to show you, you know, there's of course several examples of cases of where you can find parallel data. For example, the United Nations produces output in 6 languages, right? English, Chinese, Arabic, and so forth. The Bible, for instance, or the Quran might have been translated in many languages of the world, as does, you know, literature across the world again. Or, you know, you might go to a this is from a menu down the street, which is a Chinese restaurant that has the Chinese recipe, the name of the food, and the English one. One interesting case is this one. So have you guys heard of the Rosetta Stone? Okay, Leon has. So basically, the Rosetta Stone was a rock. Basically, this is a photo of this rock that had inscriptions like of text in 3 different scripts. Okay, one of it at the bottom was ancient Greek. All right, and because ancient Greek had survived in the form, and nowadays it's modern Greek, like, you know, the language that I grew up speaking. This is a language that we could understand. Okay, now in ancient Egypt, there were 2 scripts, the hieroglyphics and the demotic script, which, however, we didn't know how to read, right? Like in the 20th century, in the 19th century, in the 18th century, people had forgotten how to read these scripts. However, because these texts are parallel, so we figured out that they're basically saying the same thing in 2 different languages, like 3 different scripts. An archaeologist was able to essentially decode, like, you know, decrypt, if you wish, these 2 scripts by looking at correspondences between the Greek that we could understand. So they actually started by looking at named entities that we have mentioned before, like the names of kings, like of the pharaohs and so forth. And then they realized, oh, like, you know, this symbol in the hieroglyphic script corresponds to this syllable in Greek. And going forward, then they were able to actually decode these 2 scripts, and now we're able to read them, right? And the important thing here is that this data was parallel, right? So the idea is that even though we cannot understand this exactly, the fact that we have an additional piece of information that's parallel to it allows us to decode it. Okay. Yes. Yeah.
Do you know if they used Coptic in helping to decode this, or was it already dead by the time?
I don't know, honestly remember the story. I think that the person who decoded that, I don't remember his name, I'm sorry, was fluent in Coptic, so that might have helped. Because maybe Coptic is like a remnant, is like there's a continuation or something with the demotic script, but I'm not sure. Okay, so that's something to look up. The name of the guy was I'll find it and I'll send it to you later. It's a super interesting story. Okay, cool. So this idea, if we try to formulate it a little bit with probabilities, falls under this like noisy channel model. So basically what we want is a model which, given this confusing foreign sentence, let's say it's French, we want to produce the most probable English translation. Okay, so we want a model that will give us the most probable English translation given this French sentence that we don't understand. Okay, now this, with a little bit of the very basic Bayes rule, you can rewrite the probability of E given F as this fraction here. And if we're still only caring about finding the most probable sentence in English, then we can drop this denominator, right? Because it doesn't affect our computation. And basically, we can decompose this and say, we want the sentence in English, all right, which has the highest probability combining these 2 ideas. The first one is the translation model. You can actually see my mouse, right? My cursor. Okay, cool. So this first one is the one that is the translation model, right? And the other one is what we call a language model specific to English. okay? So let's see each of those individually. The language model, this P of E, will actually score and tell us whether the translation is fluent, and grammatical, right? And you can use any model for this type of language model. It can be, and who knows what an n-gram language model is? Okay, cool. So yeah, everybody is on the same page. So it's basically a way that we have for scoring fluent and also common sentences, giving them a high score compared to disfluent and grammatical sentences. Now, the translation model is basically giving us a reverse translation probability. Remember, what we want is the best E given F, right? But instead, we will move over the best, our translation model gives us the probability of F given E, okay? And this will ensure that our translation will be adequate given the source, right? The French sentence. So, on the language model side, you might just fail because you might have rare words or weird structures on the sentence, but that's not the main important point here. The main thing is, if you have a lot of data, we can have a pretty good language model. So we will focus more on the translation model. So again, we need the probability of translating an English sentence into a foreign sentence. Right now, it's the opposite. So let's say we have this French sentence. Je voudrais un pot de fromage, if you'll excuse my very bad French accent, which actually means I would like a little bit of, or some cheese, all right? And let's say we have 3 candidate sentences and we want to give them some probability. I would like some cheese, I would like a little of cheese, or, there's no train to Barcelona, whatever. And ideally, our translation model will score the ones that are actually pretty good translations higher than ones that are completely irrelevant to this sentence, right? So fromage is cheese in French. Un pot is one piece or like a little bit. Je voudrais, je is I, voudrais is would like, and so forth. Okay. So how does this look like? So one is how do we assign these probabilities? All right. One thing that we could do is just operate at the sentence level, right? So let's say we have a bunch of parallel data, and we count how many times an English sentence is also a translation for a French sentence. Okay, that's something that we could do if we had a ton of such parallel sentences. But of course, this is clearly not good, right? It's not optimal. There's an infinite number of sentences that one can utter in either languages. So we cannot really enumerate all of the possible sentences. So computing this at the sentence level is really not the way to go, because it will not generalize in your inputs. Instead, let's focus and break sentences up into the things that they made them, right? Which is words. So how do we translate a word? Let's say we can look it up in a dictionary, and we have this German word house, which very conveniently also means house or home or household or shell in English. And this means, in the dictionary, we will get several possible translations, right? Perhaps there are different word senses or different registers, or slightly different domains. And in this example here, house and home are both very common translations for the word house in German. But shell might be very specialized, because the house of a snail is its shell, right? It's what we call a shell in English. So if we wanted, let's say, to translate an article about snails from a biological journal, or from biology, or like evolutionary biology or whatever, then we would want to be able to select shell when we see the word house, most likely, if it refers to that, right? Does that make sense? Cool. So now let's say we look up at how common each of those in the English side are, and now we can get a maximum likelihood estimation of what is the probability of each of these English words given the German word house, right? So let's say we have 10,000 instances of house, or like 1,000 instances of house, and almost like 70% of those are translated into the English house. 28% of them are translated into home, just 1.4% into shell, or 1% into household, right? And this is something that we can kind of like estimate of like a dictionary and a bunch of just counts on monolingual or parallel data. Does that make sense? This is something that we would want to be able to have. The question is though, how do we generalize this over sentences? Because remember, what we want is to score sentences. But now what we were gonna do is we're gonna score sentences by scoring the translation probabilities at the word level, all right? So we have E and F, the complete English and let's say French sentence. And we're gonna say E is a sequence, you know, of these words with length M. And the French sentence is a sequence of N French words, all right? So now we're gonna decompose this into a lexical translation model that will say that each English word has been generated from exactly one word in French, right? And that will imply that there's a latent alignment, which will tell us which is the French word that generated the English word, right? In the previous example, we would want fromage, the French word for cheese, to be the word that generated the word cheese. Does that make sense? Yeah. So now, if we have these alignments that I will show you later, now our translation decisions will be conditionally independent of each other, right? So if I go back here and I told you, I want, je voudrais un pot de œuf, which I think is egg for in French, right? Now, the translation probabilities for I would like some would actually be the same, right? But I would like some egg would be conditioned on this alignment that we would have right here. I think it's better if we look at an example here. So, you know, so assuming that we have this latent alignment variable, now remember how before we had F given E, which is what we wanted to follow to model. Now we will decompose this and then we'll say for F, we will have an alignment. And now we will generate each of these English words given only the aligned French word. All right. So this is how this looks like. And this is what most people focused on modeling for the first 10 years of machine translation in the 90s and the early 2000s, right? So translating words wasn't the problem. The problem was putting them in the correct order, right? So here's what the alignments kind of like look like. You can visualize them by drawing links, right? So there's the English sentence, the house is small. And in German, you can say the exact same thing with das Haus ist klein, right? Which literally the house is small, okay? So you can represent the alignment as a sequence of vectors of these positions that tells you that the English word in position 1 was generated by the German word in position 1, or the English word in position 2 was generated by the German word in position 2. Let's see how reordering might mess this up. So let's say we have reordering, which means that between languages, there's different word orders. So let's say that we had, this is actually a very valid German sentence that says the exact same thing. Klein ist das Haus, which says small is the house, okay? Now in this case, what you will say, the alignment is again the same, right? Because klein is a translation for small, even though there's reordering. And now the alignment will say, oh, look, the English word in position 1 was generated by the German word in position 3. The English word in position 2 was generated by the 4th German word. The third English, like 1, 2, 3, the third English word was generated by the 2nd German word. Okay, is that kind of clear? Cool. So this is what we would be modeling, but the problems don't stop there, right? There's no guarantee that the two sentences between two languages will have the exact same length. So for example, one source word may not be translated at all, right? So for some reason, maybe, you know, like an article might not be needed in a language. So you might not translate a word here. So you might have this type of alignment. You might also insert a word, all right? You might have something that, you know, das Haus ist klein, but then a translator might produce the sentence, the house is just small. And now you need to explain, because we said in our assumptions in the very beginning, we wanted to explain where each English word came from. Okay, so, you know, the came from das, house came from the German house. Where did just come from, right? And the answer to this is, in our modeling, we will typically assume that every source sentence also contains this additional null token that will allow us to be able to have a proper probability model, including this null token. So now in this alignment, the fourth English word, the word just, was generated by this null word from German. All right. Ayole, I saw you had to log back in. Do you have any connection issues or something like that?
Yes, I changed the system. So I'll join when I want to use the class session. I'll join the other system.
Well, you kind of broke up in the very beginning, but I hope if there, can you text on chat just to make sure that everything's fine?
I swapped my system, so I'll join with the other system when you want to have our session. So I'll use the other system just to conserve battery.
Ah, okay. All right, cool. All right, so let me continue. So, okay, so we can have words inserted when we translate from one language to another, but we also might have one-to-many translation, right? One source word may get translated into more than one target words. So let's say this is a slightly modified sentence that in English says the house is very small, but in German, this is the way to say this, das Haus ist klitzeklein. So this is a single word that would be translated to very small. So now these English words, both the fourth and the fifth English words, were generated from the fourth German word, okay? A problem which we have not allowed in our assumptions is many-to-one translation. So collapsed here, the house collapsed, cannot only be attributed to a single German word, but in fact, you know, in our source, we needed two words to describe that concept. So, you know, the issue is that, you know, might not be able to translate one as a lexical unit always. And what happens here is not clear, right? Because in our assumption in the very, very beginning, we said that each English word must be explained by exactly one German word, okay? We'll basically, the way to avoid these problems is by using models in both directions. We will learn an alignment from English to German, and then we will also learn an alignment from German to English, and then we will combine them in order to find out what are the most likely alignments. So the most simple, the simplest lexical translation model is called IBM Model One, that makes very simple assumptions, such as the fact that the alignment decisions are completely independent, and the alignment distribution of each alignment position is uniform. The reason that it's named IBM is because it was originally proposed by some people who were researchers at IBM in a seminal paper. And we actually have 5 IBM models. It's IBM Model 1, 2, 3, 4, 5. Okay, that IBM has the simplest assumptions, and then the latest models add more and more constraints and make the models more expressive. So let's see how the simple model 1 looks like. So we have this simple German sentence, Das Haus ist klein. So for each position, I should have animated this better, but for each position, we will go and we'll say the alignment. Let's say we will sample, let's say, an alignment, and our alignment will be 1 1 2 2 3 3 4 4. And now, given this alignment, we will generate a single word here for each position. And from the translation model, we will get, let's say, these words, and now we will score this sentence, the house is small, with an English language model. And since this is a grammatical model, then our language model will say, yeah, that's a good sentence. What if we had sampled a different alignment? Let's say we had sampled an alignment that says 1 2 2 3 3 4 4 1, right? Because for whatever reason, we assume that there should have been some reordering. And now we would have an English sentence that would say, house is small the, right? Which the language model would basically score with a much lower probability. And that will allow us to find the best translation model, the best translation given, the best translation sentence given the translation model and the scoring from the language model. Now, we still haven't talked about how we can actually learn these parameters of the word level probabilities for translating from French, a French word into an English word. And the issue is, this is a bit of a chicken and egg problem, right? If we have parallel data and we know the correct alignments between every single word, then we can very easily just count how many times two words are connected through an alignment, and compute probabilities, right? At the same time, if we actually had translation probabilities, it would be even easier to actually find the most likely alignments. Does that kind of make sense? Right? So if we know that fromage is the word for cheese with very high probability, that would help inform our selection of the alignments and inform the rest of the alignments that we would learn if we have some parallel data. So the solution to this is to use the EM algorithm. So can you very quickly raise your hand if you have heard of this or used the EM algorithm before? All right, Tanmay has. All right, so I'll try to give you the general idea, mostly because the things that we're going to be talking about are already implemented in almost all toolkits. And we're actually going to run an example that implements this. So you won't have to implement it yourself, although it is a really, really good exercise and for understanding this. So the way that this looks is that by given some parallel data, you would pick some random assignment of the alignments, of the parameters, sorry, of the probabilities, right? Or either random or uniform. So now you have some probabilities, and now given these probabilities, we are going to produce some alignments. And now given those alignments, we will recompute probabilities. And now with these probabilities, we're going to recompute alignments and so forth, all right? So the main idea is that if we have enough data, these expected alignments that we can get will keep getting refined, and eventually after a few iterations, you don't need to do this. Usually you don't need more than 5 or 10 or 20 iterations tops. You will converge to a point where you will have pretty good alignments and pretty high probabilities, and these won't change from one iteration to the other. So here's what this kind of looks like. Let's say we have English and French, all right? And we have these very simple sentences or phrases. So we have the English sentence, the house, which in French is la maison. And we have the blue house, la maison bleue. And we have the flower, la fleur, or something like that, Now, in the very beginning, in our initial step, all alignments are equally likely, right? So we're saying, well, we don't know what should align to what. So we're going to give uniform probability to all of them, right? And now we're going to compute probabilities over these expected alignments. Now, because we have several examples over several sentences that are repeated, you can see that, you know, it's kind of like the process that you kind of did in your mind when you were trying to order coffee in Maori in the very beginning, right? You can see here that la is aligned to the, here, here, and here, but la is aligned to house only 2 times, and la is aligned to like flower or blue only once, right? So even with uniform probabilities, if you compute all of those, la is more often aligned with the than it is with any other word. So after a single iteration, because we have updated our probabilities, now if we recompute the alignments using our probabilities, some alignments will have a higher, will be stronger essentially. So like this la and the will have a higher probability. Maison will have a higher probability to be aligned to the or house than blue, and similarly here. So now, given these alignments, these expected alignments actually, we're gonna recompute our probabilities again and do another iteration. And now, as we keep going, some alignments will become even more apparent. So basically, you know, since la and the is so probable, so high probability, then it makes sense that whatever is left, you know, this is not hard-coded, it's just something that is learned, right? That whatever is left becomes also stronger. And so through this pigeonhole principle. And similarly, you know, maison and house here will become more likely. And eventually, if you do another iteration, blue and bleu will also become very likely. And eventually, at the very end of your parameter estimation, you should have something like this that will give you basically pretty high probabilities for what are the correct alignments. And these are the probability of these word level substitution, where la and le, which are actually French articles, translate to the with high probability. House and maison are translations of each other with very high probability, and similar from blue and blue and, well, you get it. So let's, so this is something that we can do given parallel sentences, okay? Now, how do we use this? Let's, if we have all of these probabilities, okay, now we can use these alignments to extract word level and phrase level translations, right? So if I ask you, what is the translation of the, you can look at the alignment and say, oh, it's just la or le. But if I ask you, what is the probability of, what is the proper translation of the phrase, the house, you can again look at the alignments and pick everything that is aligned to it and say, oh, it's la maison, right? And the same here. Or blue house, you would look at this part and get the phrase. So you can use these chunks in order to translate phrases. So, and this is what happened in the mid-2000s with phrase-based NT. Now, the idea is given a source, this is Spanish, that says, Maria no dio una bofetada a la bruja verde. Maria did not give a slap, like did not slap the green witch, okay? Now, what we will do is we will get phrases and they will get possible translations for each of them. So let's say our translation model will say, Maria can be translated only to Mary. No can be translated to not, did not, no. Dio can be translated to give. But we also have another segmentation that gives us this complete phrase that says no dio, which can be translated to did not give, okay? Una can be translated to a, bofetada can be translated to slap, You can similarly see another phrase here, una bofetada, that can be translated as a slap. We can also have a bigger phrase, dio una bofetada, which is give a slap or slap overall, and so forth, right? So we can do this for each word, for each phrase, if we have it in a phrase table that we have extracted from these parallel alignments. And now all we have to do is now we want to find the translation that is the most likely given our English language model. So all we'll do is we will score each possible path, like Mary not give a slap by the hug body, or Mary not give a slap to the green witch, or Mary did not slap the green witch. And as you go forward, like you will score all of these possible sentences with your language model, and you will keep the one that has the highest probability, which in this case will be the one that's highlighted in green. Okay. Now, another thing when it comes to alignment, and then we'll go into playing a bit in our terminal with this, is to assume some type of prior, right? So rather than saying that all of these alignment decisions are actually uniform, then perhaps you would want to learn an alignment that kind of like follows a diagonal, right? So especially if languages are close or similar to each other, you know, English and French will follow the same word order, right? You'll have a subject, a verb, and then the object. So you can make your alignment better by imposing this type of priors that say, hey, I would like you to align these sentences, but also try to follow along in the diagonal. Or you can try to impose some form of syntactic structure, taking into account the syntactic trees that, you know, the structure that the two languages might have, and create rules like these, so that, you know, I cannot read Chinese, but you might have phrases like this that says one of the X is something you translate as X and this symbol here. So before we go to the next slides, I would like us to do an exercise with training an alignment model. Is everybody here? So let's open up, like log in into Clio, I guess, and I'll start sharing my screen again. And we will go and download a really cool library. Where is the chat? All right. So let's go and download this fast align library, so what we'll need to do is git clone this command. And then this is a C++ library, so you don't really need to do this inside your Python environment, but I'm just already here. So
and Antonis, could you zoom in with your
camera? Oh, sorry. Yes. Is this big enough?
Yeah.
All right. So we did this git clone, which I have already done, right? And you were able to get the code. And then all we need to do is run these very simple four very simple commands that I sent. So make dir like a build directory cd in there, run cmake, and then just make, and this should just call build your
the code into the chat option so it's easy for.
Yeah, I just did. It just make dir build cd build cmake dot dot and then make. Does this work?
So I don't have CMake installed.
Oh, it's not installed in your machine?
Yeah.
Oh.
And I don't think I can install.
Yeah. Oh, because you're in a different machine.
Yeah.
Well, actually, so what, do you have a desktop or a laptop or something?
Yeah. I'll just try it on my machine.
Yeah.
Yeah.
I remember the first time I installed it, I got some errors, like it couldn't find like G++ or something like that. So if you're getting something like that on Clio, let me know.
I'm good here. I have it. I ran all of them.
Okay. Kathleen and
Quick question. Are we CDing into the first align?
yes.
Okay. Then we're
Yeah.
making the directory build.
Yes, sorry. So yeah, before these, you should CD into first align.
Okay. Okay, I'm done making.
All right, so you should be seeing something like, you should have this first align command installed now. And now this is super easy to run. The only thing is that you need to provide it a parallel text in a form that looks like this. I have some data that I'll show you how to get. So I just took a parallel corpus, which is between some European languages. And these are parallel sentences between English and Latvian, okay? And these are available under, I'll put it on chat. So for the people on Clio, then you should be able to just copy this data into your local directory.
I can't see. Oh, it's okay. Never mind.
For you, let me see what I can do. Let me see if I can very quickly just download it and send it to you. Okay.
Hello, Anthony. I'm having issues with the directory also here for the build.
So
Yeah,
you run. So you run git clone, right? And then you do cd in first line.
Okay.
So what is the problem? Tanmay, I'm sending you a drive link via email for the Europal data. Okay.
All right, thanks.
Okay, Ayole.
Yeah, I'm here. I'm having a bit of issue here, but I'm trying to sort it out.
Would you like to maybe share your screen?
Okay.
Okay, wait. So, all right, so can you go out of the build directory? Can you do cd dot slash, oh, with a space between the dot.
Right?
No. So go up one directory. So cd space, yeah, no, space. Without the slash. So this. There. That, okay. All right, so can you do like ls so that we can see, like you should have downloaded fast align, right? So if you write.
As a make directory, right?
Yeah. So. No. Wait. So did you do the git clone thing?
Yes, I did the git clone thing.
All right, so then you need to cd into fastline. So do cd into that downloading into that directory.
This, right?
Yes, cd space, cd space, and then you need to tell it into which directory. So cd into, so if you type fa, you don't need the slash. So if you type fa and then fa, like fast align, and then I have sent it in the chat.
Okay, thanks.
So you need to go into that directory and then run the 4 commands that I sent here. They work now? Yes, no? All right. Well, Well, I'll keep going. Worst case scenario, you can just follow the things that I'll be doing on my screen, and we can sort it out later, Ayodele. Okay.
Yes, thanks. I'll do that.
All right. Okay. So now, basically, were you guys, Kathleen and Leon and Tanmay, were you able to get the data too? Yes. Okay.
Yes.
All right. So this data, as you see, the only thing that it has different is that it separates the two sentences, the English and the Latvian one, with these three pipes. All right. This is kind of like standard in machine translation, but it's also kind of like completely arbitrary. And now what you can do is run a command like this, which will produce the, yes?
Do you mean to be showing your screen right now?
Oh, yeah. I'm sorry. Good catch. Thank you. All right. So you can see my terminal again now, right? Okay. So, yeah, so the only thing separating these two sentences is just these three pipes, which is kind of like arbitrary, but this is what fast align expects. And it's kind of like typical for machine translation to just present parallel data this way. So now we can run this command that we just created, that we made, substituting for the text that we have, in order to get the forward alignment. So the forward one will take us from Latvian to English. So I'll point to the data here. You'll point to the data wherever you put it, right? And then if you run this, it will start doing an initial alignment. Oh, this is gonna take a while. So let me know if you're seeing something like what I am seeing here. Kathleen?
I'm copying the command.
Oh, right. Let me. Yeah.
So I'm going to ask David to install CMake on the GPU, but is there any other software that I would need?
For fast align, no, not really.
I meant like potentially.
Oh, yeah. So in about 30 minutes, we're gonna use PyTorch and JoyNMT. But for these, I think because I have run stuff on the same on patient, right? Then I don't think you'll need anything else for these.
All right.
And I mean, fast align is something that you may or may not need for your internship. So, so basically what this does, remember when we mentioned the EM algorithm and how you can do several iterations? So basically what it does, first the initial pass and then iteration 1 and then iteration 2, and it prints out some probability scores. Well, and there's a bunch of things that you could have sent out to do, like with different flags. But the most important thing is that this is kind of running. Now, this is taking a while. I should have tried. I should have only run it on like 10,000 sentences rather than all of them. Yes, Kathleen.
So is the idea that you don't have text that is sentence aligned, and then this EM algorithm or fast align helps you align that?
No. So actually, this approach requires that you have sentence aligned data. And these alignments will now, so we have the sentence alignment, and fast align will give us probabilities and like it will give us basically the links between the two sides of the sentences. Does that kind of make sense? So if we look here on what the output is, what the output looks like, it's basically this type of things. All right, so for the first pair of sentences, let me just kill this because I actually have run this before, and I will show you how the output looks like. You can keep yours running. So or maybe I didn't have it running. Where did I run it? Let me show you real quick how this looks like. So let me do, let me just get 10,000 sentences from the data. And put them in a temp file. Okay, and then I'm gonna run this real quick so you see how the output looks like. So now I'm gonna tell it align these temp data. This is now much faster. All right, so let's see these sentences, right? So these are the first 10 sentences. And let's work with the easy ones, right? These are very short sentences, and interestingly, this is not Latvian, this is Italian. Anyway, so lesson for not all data are super clean, even the ones coming from the European Union, if anything. So okay, so this is the data, and this is what the file that we created looks like. Okay, so this gives us the links between the source and the target, right? Because we did the forward alignment. So let's look at this sentence, which has 2 Latvian words, 3 English words. And we have this alignment here that tells us that the first word, well, we're counting from 0, right? The first Latvian word is aligned to the first 2, 0 and 1 English words. So sedes, if I pronounce it correctly, is closer of, and slegsana, like the second Latvian word, is aligned to the third English word, sitting, okay? And this is the forward alignment. Now, we can also run the reverse alignment, which will go from target to source, and it will produce, let's run it and see what it will do. All right, let's have our sentences again here. And now let's print the reverse alignment. And now it will be going from here to here, right? And now in this sentence, in this last one, you'll see that we need to explain closure. And this tells us that closure 0 is aligned. Oh, maybe I explain. Yeah, my bad. So yeah, so this is just, the probabilities are computed in the opposite way, but these are still presented from like Latvian to English. So these are the ones that, closure now is aligned to sedes, and sitting is aligned to slegsana, like 1 to 2, but we don't have the explanation for this word. Okay. Now, the next thing that we can do is actually combine these 2 alignments with this extra tool. Oh, here, that we also built when we built oops, let me put this down into like phrase table. And now this phrase table will actually combine the two. No, it's not exactly a phrase table, but these are like it will combine the forward alignment and the backward alignment into one that combines information from both of them by expanding over phrases that have been discovered perhaps one in one direction or the other. Okay, so this can be super useful. This is super easy to run because it's really just 3 commands. But now having that information and writing like a simple Python script, we can convert that, which I haven't done this. You can probably easily do it if you need to. Now we'll be able to convert these into like probabilities from words, right? Because we can look at the indices here and we can count how many times status is aligned to closure or closure of and so forth, and basically find word level translations of each other and convert. And now given these alignments, we can now count how many times these are connected and compute the probabilities for our translation model. Okay, is that somewhat clear? Or at least, you know, given parallel sentences, now you know which very simple 3 commands you need to run in order to get alignments between these parallel sentences. Okay, cool. So now let's go to some more modern things, because let me go back to my presentation. Because this is what we were doing up until like 2013. Oh, there it is.
So then, quick question, is fast text using the EM algorithm?
Yes. Yes.
Okay.
So it's using the EM algorithm. That's why it did this like 1, 2, 3, 4, 5 iterations. But what it additionally does, it puts on the prior along the diagonal. And that's why it's actually faster than doing the complete pipeline. So fast text is a really good option for languages that are similar and follow more or less the same word order. If you have to align languages that do not follow the same word order, I would suggest that you use some other tools like Giza++ that I haven't shown, which actually does a cascade of the IBM models. So it does like IBM 1, and then given the output of IBM 1, it initializes IBM 2, and then from that it goes to 3, 4, and 5 in order to refine the alignments, along with some other models like the HMM model, in order to actually get much better alignments. But fast align, if you have enough data and more or less related languages that follow the same word order, should be absolutely fine.
So I have a question.
So that means, okay, so that means for words that don't follow each other, fast align won't work, basically.
I mean, so it will still work because you can control how much you want to trust your diagonal prior. So there's an option that would tell you, ignore the diagonal prior. So in that case, you'll be essentially doing IBM 2, I think, or 1. But again, if you have a lot of data, then the probabilities from the actual data will overcome your prior beliefs, right? That they need to be along the diagonal. Like it's not like hard coded that the alignments need to be along the diagonal. So if you have a lot of data, fast aligning will still work. And what we define as a lot of data is debatable. So like 100,000 sentences is parallel sentences is probably enough. If you only have like 10,000 or 20,000, then you might get not very good alignments.
Okay.
Okay. And Tanmay, you had a question too?
That was my question. So I was wondering how much data would it require to give like good alignments? Because I'm looking at a lot of these tools from that angle as to what will be useful for low resource languages and what wouldn't. So you said 10,000 will be not enough.
So it actually depends on what you want to do with the alignments, right? So, you know, in the example that I had in my presentation, let me just share just with just 3 sentences, right? With just 3 sentences, you would have been able to translate like la maison and la fleur, like here, right?
Yeah.
So it depends on what is the vocabulary coverage that you want and what you want to capture. And, you know, the thing is, you know, with these 3 sentences, you're still very, you can learn to translate like common words, like in simple phrases.
Yeah.
Right. So it depends on what you want your alignment for. If you want to be able to translate complete sentences, then no, like just a few hundred sentences or a few thousand sentences are not going to be enough. If you want to have a general idea of what like the reordering looks like in the language for this particular language pair, then, you know, a few thousand sentences might be enough. If you want to learn word for word translation, it also might depend on how morphologically rich the language is, right? Because, you know, if you have a single word for blue in Greek, let's say in English, but I can tell you that, you know, blue can be translated to like 10 or 20 different forms that are basically the all mean blue, but they are inflected differently. I remember you both, I hope you'll remember David's morning talk, right? So, you know, this can vary a lot. Like the amount of data you might need will vary a lot depending on the language pair and what you actually want to be able to do with your alignments. Okay?
Yeah, makes sense.
Cool. So, all right. So let me continue very briefly and let's talk a little bit about evaluation and then we're going to go into neural models. So when we're talking about machine translation, the question is how should we evaluate the output, right, of a machine translation system? Like, how do we know how do we know that this is Mary did not slap the Greenwich, a good translation, and Mary did not give a slap to the Greenwich is a bad translation? So the central idea is that if we have a human produce, a professional translator, create a translation, then we would want our system to essentially produce a sentence that is close to that, okay? And of course that it kind of makes sense, but it's also kind of sketch if you think about it, right? Because there's always more than one ways that you can translate things, especially in languages that have like free word order or are morphologically rich. So here we'll just talk about the most commonly used metric, which is called BLEU. And the idea is the following. Let's say we had a sentence and we gave it to a translator, and they produced this reference translation that says, it is a guide to action that ensures that the military will forever heed party commands, right? And then we gave it to a different person and a different translator, and they produced a second reference, and the third one produced a third reference, okay? So we have 3 really good translations of the same source sentence. And here's what our candidate translation is, the one that our system produced. Now, what we will do is we will see which words in our candidate translation match exactly the reference translations that we might have. So the words, it is a guide to action, actually map exactly to one of the references, which doesn't map to this sentence, but it maps to this reference and so forth. So out of the 18 words that our system produced, we were able to find 17 of them. So we can say, hey, we have a unigram precision of 17 out of 18, okay? Now, of course, just doing this over unigrams, like single words, is not super useful. So what BLEU does, it does the same thing over bigrams, and over trigrams and over foregrams. So if it manages to find a complete foregram, like the foregram, a guide to action, then we get a point. If we try to find the foregram guide to action which, because this we cannot find it, like guide to action, we have the foregram guide to action that, but we don't have guide to action which, then we don't get a point for guide to action which, and so forth. Now, and then we have precisions for unigrams, bigrams, trigrams, and foregrams, and we combine them together into a single score. However, this still has issues, right? What if in this extreme example, right, we have these two references, the cat is on the mat, or there is a cat on the mat, but our system produced a really bad translation that says the, right? And if we only focus on precision, each of those words actually appear in the reference. So we would have a precision of 100, like 100%, which is not something that we want. So the solution to this is we exhaust the reference words once they are matched. So if we match the to this word, then we cannot match any other of the candidate words to this particular word, right? I think that's easy to follow, right? It's very clear. So here in this example, we would probably, if we include this solution, we would get a precision of 3 out of 7. So this the would match with this with this perhaps with this, and everything else would not match with anything. Okay. But there's now you could say, hey, maybe I will just produce a very short translation. In this extreme example, our system will only output the, and we will find it in the reference translation, and we will have a precision of 100. So how do we deal with this? We also add a penalty if the hypothesis, the candidate, is too short. So on top of these precisions, we will also have a brevity penalty that will say, hey, if the length of the hypothesis is much shorter than the length of the references, then I'm going to penalize that heavily. And in combination, basically what you end up with is this computation that combines n-gram precisions for unigrams, bigrams, trigrams, and foregrams times a brevity penalty. Okay, so again, you don't need to implement these. There are toolkits out there like Sacro Blue that will end up installing later that will automatically compute these things for you, given the reference and the hypothesis of your system. So, okay, so now we know how, yes.
So it said that you get a point.
Let's go, Tanma, you go first.
Yeah, so it said that you get a point for, I'm clarifying. So you said it gets a point if there's a unigram match or bigram match or trigram match or foregram match. Each of those gets 1 point, or I'm wondering, is a higher match more should be, so if there's a foregram match, it will also include 2 trigram matches.
Yes.
All right. Okay. Yeah.
Yeah. So this is not taken into account though, right? So basically, you know, let me see here. In this example, although this is kind of long, let's see here. So we have 18 unigrams. That means we have 19 bigrams, like it is a, like, well, actually, start of sentence, it is a guide, right? So we'll have something like, the only bigram that we will not find is we will not find 2 bigrams, right? The always obey and obey the. So we will have a bigram precision of, say, I think it's 17/19 or like 18/20, one of the two. Okay.
I mean, you also won't find some other bigrams.
Oh yeah, you're right. You won't find action which or which ensures. Yeah, you're absolutely right. So yeah, but the point is, you know, we'll have this high unigram precision. will have a slightly lower bigram precision. In most cases, almost always, this is what will happen. You'll have a high unigram precision, a lower bigram precision, a lower trigram precision, and a much lower foregram precision. And these all get combined together, right? But the thing is, you want this in order to be able to be sure that you properly translate phrases and stuff, because, you know, the unigram basically doesn't take word order into account, right? And in theory, you could also have like 5 grams and 6 grams and 7 grams, but then it gets just too big and it becomes too sparse. So, you know, the general idea is just up to 4 is probably okay.
And having a really high n-gram would also penalize generalized outputs. Like you don't
Correct.
always want an exact translation.
Yes, yes, exactly, because there's not always a single correct translation.
Yeah.
Ayodele, you had a question too?
Yes, it seems you've answered it. I wanted to ask that, does it take word orderings into consideration when it's making that?
Does it take what into consideration? The word order?
Yes, you've answered it. Just.
Yeah. So yeah, it is implicitly taken into consideration by looking at 4 grams, right? Where the order is in there. Of course, okay, blue is the metric that most people use. It doesn't mean that it's the only metric, right? Because, you know, it's very easy to calculate, and it's very good for comparing systems, especially. But you can see that with this idea that it has like an exact match for unigrams, bigrams, etc., it can be bad for some languages, right? So why should the system be penalized if you only have, let's say you only have one reference that says the cat lives in the house, or like the cat stays in the house? Why should you penalize the system if it translated into a cat stays at home, right? Home and house are not the same unigram, so blue would be penalized for it, and the bigrams and trigrams and so forth would also be penalized. But this is a valid translation. So there's other metrics like Meteor that try to take into account like synonyms and stuff like that. Or, you know, there's also other metrics that are more appropriate for morphologically rich languages. So we can talk about it later during your internship if you need anything like that, okay? If you're not working machine translation. So, okay, so let's go into neural machine translation. Can you quickly raise your hand if you kind of like know what the deal is with neural and MT and neural models? So that, okay. So I guess we have about a 2 out of 4. Let's see. Oh, okay, 3 out of 4, but that's fine. So I'm gonna give you a very brief introduction into this. And because if you're interested in machine translation, you're gonna end up like using them, then you learn more by running the tutorials and reading the papers. So basically, these phrase-based systems that we talked about before were cutting edge up until about 2014. But since then, the research has moved to neural models. So what is the idea of a neural model? The neuron is very loosely inspired from the way that human neurons work in our brain. So the idea is that we have a bunch of inputs and they somehow get combined, let's say with some weight, and then we have an output, right? So this is very simple, right? The output can be just basically a weighted average of all the inputs. This is exactly what we have here. Now, in our brain, this is not exactly what happens. Well, this is not what happens almost at all, but in a very simplistic approach, like representation, what happens is that the neuron fires, like sends an output, if this weighted average is above a threshold. So a single neuron like that will, given this function that describes the threshold, will fire if its input is, say, like over 1, or, you know, it will fire a -1 if it's below -1. Okay, so this is the very basic model, which basically combines an aggregation with some type of like function that it is non-linear in terms of how it actually fires. Now, this, if you combine a bunch of neurons here, then you have a network, okay? And very nicely, the way to formulate this mathematically is through like matrix multiplication, right? So we have this input and we have this matrix of weights that describe the weights for each of these neurons. Then the output for each of those as a vector will be this matrix multiplication, okay? And on top of that, we will also add the nonlinearity. Now, deep neural networks essentially just do this over and over, right? So we have these neurons that provide input to the next layer and so forth. So the output of this layer, Z, will be a nonlinearity times now this and the output of the previous layer, where the output of the previous layer was this times this through this another nonlinearity, okay? So this is fairly simple. Now, and this is like just a very simple, like a bunch of inputs and a bunch of outputs. Now, for sequences, like for sentences, we have what is basically recurrent neural nets, so that we do the same computation for each input in our input sequence. This is not a very nice example, but I'll explain later what this happens. So we have a bunch of design decisions that we need to make. So how should we represent our input and our output, right? In images, if you do image recognition for something, your input is a square with pixel values, okay? In language, like if you have a sentence, your input is a sequence of words or a sequence of characters or a sequence of subwords or sounds, right? If you want to do sequence speech recognition, your input is actual sounds. It's a sequence of like, you know, raw audio. So we need to decide how we're going to represent the inputs and the outputs. And then we need to decide what type of architecture we're going to use. How many layers are we going to use? How many neurons will we use in each layer, and so forth. So going into representing language, one very simple way of doing this is using one-hot vectors. So let's say we have a list of all the words that appear in the English vocabulary, okay? And we say that the representation for each word will be this one-hot vector that has an 1 in this position, all right? I think that's something that probably you have seen in the past. This is very super simple. So the advantage of this is that it's very simple, but now this kind of like misses the nuance that actually lies in language, right? We have no indication here, you know, with this vector that dog is an animal, or that dogs and cats are both like, you know, animals that might be pets, or like that a house and a home are essentially synonyms. So a better way of doing this is to use distributed representations, which are again, are just a vector, a sequence of numbers. But now, rather than having a very exact mapping that tells us, you know, I will only have a value in position 0, in position 1, if the word is aardvark, whatever that word is, or I'll have a value in position like 123 if the word is dog. We will have a bunch of numbers that will encode features of words, okay? And this can be character engrams, this can be morphological features, this can be like features regarding synonyms, features regarding whether something is a verb or something is a noun, and so forth. In the very end, and you know, you end up with just essentially a vector with floating point numbers. You'll talk a lot more about this tomorrow with me and Peg Fei tomorrow afternoon about representations. But the main idea is that I wanted you to take away is that we can represent each word, or in fact, each thing that we're inputting as a vector of numbers, okay? Now, how do we, now that we have decided that that's how we're gonna represent our input, in our case, in machine translation, our outputs are also sequences of words or of characters. So we're also gonna represent them like that. So now we have the representation of the input and the output. And now we want to be able to train our neural nets. What does training a neural net mean? What it actually means is figuring out what the values for these intermediate parameters should be, so that so that given an input, I get a correct output. Okay? So the way that we do this is by basically training the model. Is we give it examples and we tell it, hey, here for this input, I would want you to actually produce this output. All right. And basically we do this by an iterative procedure for this supervised approach, where given a paired input and output, let's say parallel sentences in our case that says La Maison Bleue should be translated to the blue house. You give the input to the network, La Maison Bleue. You take its output, which can in the beginning will be absolutely garbage, and you're gonna see how well it compares to your correct output, right? And this is what we do here by computing this loss. So by computing these laws, we can say, oh wait, you produced or the green apartment, but I wanted you to output the blue house. So then we compute differences mathematically that tells us here's the loss that for this particular example that you go for this particular example, and then we use a technique called backpropagation that will basically go back to each of those little parameters. So we went forward. In the forward, we produce the output, and then we will go back and update each of those parameters so that they would have produced something that's closer to our desired output. Is that kind of clear? The main idea is that, we give it examples, we see what the model produces for each input, and then we change its parameters just a little bit for each example so that it will be more likely to produce the desired output. And by doing this over and over for many epochs over several examples, then eventually we end up with a model whose parameters learn to make the transformations that we wanted to make. So for the rest of the slides, I'm gonna simplify this notation to denote neural nets. So basically think of this as like a block of layers. So the way that this looks in neural machine translation using RNN recurrent neural net models is using this encoder-decoder approach. So the idea is we have an input sentence that we represent each input, let's say each word, with a vector, as we described before. This can be in one hot vector, it can be a distributional vector, and so forth. And then we put each word through a network, which actually also goes through the sentence from left to right. I guess from left to right, right? And now when we're done right here, we have some representation. We have essentially another vector, just a bunch of numbers that have encoded all the information that we have in the source sentence. And then we have a second component, the decoder, that receives that information and now tries to decode and produce the output, again, one word at a time. Okay. Now, this was the first.
I have a
question
about this slide. So in the decoder, as I understand it from this diagram, a word has the knowledge of, does it have the knowledge of just the last word or all of the words that were generated?
In the decoder side?
Yeah.
So the nice thing, well, I didn't go into more details, but the nice thing about the recurrent neural nets, especially if you implement them with some specific units, is that you have a vector that's called the history or like the memory that gets propagated from step to step, right? So here, if this is like an LSTM, you have a vector that, you know, first you have only read I, and then you read and then you update this memory, this history. Then you have A, and then you update its student, and then you have the end of the sentence. So you have this one vector that has seen these 5 tokens, okay? And that's what you pass to the decoder. Now, in the beginning, the decoder hasn't seen anything in French, right? This is French, this is English. Hasn't seen anything in French. Now, when you produce the first sentence, the first word, sorry, then you feed it back in and you update your memory again so that you know that, you know, I had this source sentence, I have produced this first word, now I'm gonna produce the second. And then you feed it back in and then you produce the third. And then you feed it back in and then you produce the fourth. And because this says end of sentence, then you're done. Okay?
Yeah.
Cool. Now, this idea, of course, even though it worked great as a neural model, it's kind of like worked on par with the phrase-based model, still has some issues. So that here came the attentional model, which was a solution because if you think of this example here, what if I had a sentence here that is like 80 words? It's not super easy. And in fact, some people say it's not possible to cram the meaning of a whole like 80 or 100 or 200 word sentence into a single vector of like 200 numbers. So what we do instead is do something that's a little more natural also. Like, what if we only look at one or a few source words every time we want to generate a new output word through our decoder, right? And this intuition is very clear. And it seems, it kind of like reminds us of the alignments that we were creating before, right? So the attention model looks like this. As before, we have an encoder, which, you know, we embed our input, which means we represent each word as a bunch of numbers as a vector, and we put it through an encoder, and now we have some intermediate representation. And now for our decoder, we start with the one state. We will have an attentional model that the attention model will tell us, you know, at this point, look at this particular part of the input and produce another vector that is basically the context. And then using that context, you will produce the first word. Now you will feed back the first word, and then now you have a new state, and then you will use, again, the attentional model where you will now attend over a different word, let's say that will give you a different context vector, and then you will use it to produce the second word, and so forth. So the difference is that before, the only connection between the encoder and the decoder was this entry here that, you know, we initialized our decoder state with the output of the encoder, whereas now for each time step, we use the attention to attend over the encoder and get a single context vector that we can then use to produce the final output. Like, does it kind of like intuitively make sense? Maybe, yes. All right. Now, I assume that perhaps most of you have heard of the transformer, which is, again, the exact same idea, except applied rather than going from left to right to encode the input sentence, or going from left to right, or going from right to left to encode the sentence, which is what we have been doing. What if you actually encoded by using self-attention, essentially using all of the words in the sentence to inform your representation of every word in the sentence itself, right? So the idea here is that in language, context matters, right? If you say, I am a student, that's okay. If you say, I am a student in high school, or if I am a student at Carnegie Mellon University, or I am a student of, let's say, Graham Newbig, right? These have slightly different connotations. you could probably translate, for most languages, translate all of them in the same way, but it could be that, you know, there are many cases where you could be using different words to translate these. So let's think of an example, like the standard one is in English, the word bank, right? So if we say, I went to the bank to get some money, then you would translate the word bank to be something like the financial institution, whatever it is in your language, right? But if you say, I'm gonna go with my wife to the riverbank and have a picnic, then that's a very different meaning, because bank now means, you know, the borders of the river or whatever. So that would very likely be translated into a different word in most other languages compared to the financial bank. So by using self-attention, what we essentially do is we use the context from the same sentence to inform the representation of every context using this technique called self-attention, okay? So what we do now is we basically do the exact same thing in the transformer. We have an encoder and a decoder. Our decoder uses self-attention, and our decoder uses the same attention model as before, okay? And the only difference now is that since, you know, context matters in this language, context would also matter in this language too, in the generation side, on the decoder side. So the only difference now is that rather than having a recurrent network here, when we are generating the third word, we will also use self-attention over the generated sentences. Notice here a slight difference. When we encode, we have the complete sentence, okay? So we can, you know, we can use context both from left and from right in order to generate, in order to produce the intermediate representations. On the decoder side, we are generating from left to right, one word at a time. So the self-attention here is only informed from what we have already generated, right? So if you see the attention here for producing this word, étudiant, je suis, does not look into the future, essentially. Okay, cool. And you can see that, you know, if you visualize the attention. Yes, Kathleen.
So the encoder, decoder, the attention model, and then the transformer, are those the way you have arranged them in order of, let me say, state of the artness? And really, I'm just wondering, if I used a transformer, regardless of language, should I expect that it should perform better than an attentional model or an encoder decoder on its own, or is that going to be language dependent?
It would be probably language dependent. If anything, mostly because it would depend on the amount of data that you have and the general architecture of your model. So yes, in general, and in most cases, what happened was the encoder-decoder initially wasn't better than phrase-based machine translation, okay? But then after using a lot of data in like English, French, English, German, English, Chinese, the encoder-decoder was better. Then the attentional model is almost always better than the encoder-decoder without attention, okay? And like, you know, this is just encoder-decoder, this is encoder-decoder with attention, and then the transformer is still an encoder-decoder for the record, right? The only difference is that it's not a recurrent encoder-decoder, but it uses self-attention on both sides. And yes, everything else being comparable, I would probably expect the transformer to be better than a recurrent neural net, a recurrent encoder-decoder, which I would expect to be better than a simple encoder-decoder without attention. However, these models usually require a lot of data and a few little tricks in order to make work, in order to train properly and make them work well. So in very low resource settings, for example, it might be the case that you will not be able to train a transformer because it has more parameters, or it might have to, it might have to be big or something, like very deep, and that's harder to train. Whereas like an encoder-decoder with attention, but with recurrent encoder-decoders, will be easier to train and then get better results. So that's something that, you know, if we're interested in training machine translation systems, it's something that we keep in mind, that our best model will depend on how much data we have. It will also depend on the type of languages that we have. So far, you know, we have trained, we have only talked about like word level stuff, but in practice, you cannot have a vocabulary that covers all of the words of the language. So what we usually do is we use subwords, which you talked yesterday about with Graham using sentence piece. Does that answer your question, Kathleen?
Yes, it does.
Okay, yeah, and you know, again, if during your internship you end up like needing to train machine translation systems, we will go through this and see what works better. Yeah, quite often, you know, very often you can kind of like gauge in advance to figure out, you know, oh, this will probably work better because we have a lot of data, or something like that. But you almost always never know. If you properly fine tune and train your models, then maybe you won't see very big differences between a standard recurrent model with or a transformer model if you're in low resource settings, for example. Yeah.
I have a quick follow-up question. So when it comes to tuning a model for a language, I guess depending on the architecture, the ideal settings that you find, is that going to be ideal settings for the language, such that if I say threw in more data, I could just use the same settings, trusting that they are the best? Or are those settings dependent on like the data set and the size and stuff like that?
Yes, the best setting will most likely be dependent on all of that. So it's actually an issue, well, that we don't exactly know what will be the best. We have a good idea. If you have trained enough systems, you will know that, you know, if you have a ton of data, then if you can make your models much deeper, then you will get better results. If you have a few data, then, you know, making your systems shallower, like less deep, you know, it will be better. But the truth is, you know, there's no guarantee that something that works in English German or in English German will work in Swahili Hindi. And similarly, if something works for Swahili Hindi in like, you know, a small data set, might not be optimal for Swahili Hindi in a much larger data set if you happen to have one. Yes, Leon.
Since these only really work for you know, more high resource languages, or generally that's how it goes, are we going to be going over any sort of like techniques in order to increase the amount of data that we have, like data augmentation or anything?
Yes, yes. We are going to talk about it. I don't think we have enough time to talk about it today, but the answer is yes. Because, you know, we talked about how like we need parallel data, and parallel data, you know, even though they exist in abundance for some languages, they're also very scarce for other languages, and translations and translators are expensive too, right? It's not easy to create a new data set. So yes, data augmentation is one very good way of producing really good, of producing synthesizing data that look like really good parallel data that we can use to train these systems. And that's actually what actually makes a big difference. And we can actually make these things work even for languages where we only have like 10,000 or 20,000 parallel sentences, which if you think about it, is not too much, right? Like just the Bible has like 3,000 or 5,000 sentences, for example, or like the New Testament. You know, so yes, something to keep in mind. I don't think I have it covered in these slides, but it's something that we will end up using if we end up working on machine translation for your projects.
So just a question for me.
Mm-hmm.
So in case in a situation that we have parallel data, but we have a dictionary that just have word translation, do you think attention model will still work better, or like we have parallel?
So you have parallel data, but they are at the word level? What do you mean?
Yes, you have parallel data that is both maybe English to Yoruba, but you also have just a dictionary that just have just the word translation, like boy, what a boy is, girl, what a girl is, and you want to augment that data together to work on a particular model. Is that possible?
Let's see. So this model that I have here operates on sentences, right? And
yes.
So if you want to generate a sentence one word at a time, then it's better to use the attentional model. Now, the question, I guess, I think that what I would do if I wanted to train a system for Yoruba is if I have word for word translation, so I know I only have word level translations, okay? I also know, do I have any monolingual sentences in Yoruba? Like, do I have any sentences in Yoruba? So if I do, then you can, as Leon said, we can synthesize some parallel looking data, right? We can take the Yoruba sentences that we have and then use our dictionary to produce word for word translations, and then use that to train a neural model. And we can do the same in the opposite direction, right? Because the dictionary goes both ways. We can take a bunch of monolingual English data and use a word for word substitution to produce something that looks like Yoruba. And then we can train our model on that too. And then the interesting thing, that's what the main, really that's the main idea behind the techniques of unsupervised machine translation. What I'm talking about here is the supervised one. So in this unsupervised machine translation setting, what you do is you start with something that's like very naive, like word for word translation, like something that you get out of a dictionary. And then you use that to train a model. But now, then you do that again and again, like you translate, then you use your model to translate monolingual data. And then you go forward, like you do this like 3 or 4 times, and then eventually you end up getting better. Perhaps we can talk about it more later.
Okay, sorry, just one more follow-up question, just something. So what just explained, I actually tried it a bit, and the problem I got there was, I used the Bible, and in Yoruba, the Bible has more of the things that they are not contemporary. But we now have a dictionary where we have things like university, institution, and they don't exist in the Bible. So to really synthesize it the other way became difficult, because the unsupervised, the parallel corpus could not really give insights to what the dictionary should be.
Yes, so yeah, you touch on a very important problem, which is the difference between training and the data that we want to be using it, right? So if we want to train this, if we only have, like, let's say, training data from the Bible, then our model will be really good at translating these Bible data, this particular domain, and the words that it has seen. And you're right that it won't be good at translating other words or other phrases that are more modern that it has never seen before. However, in order to translate the Bible, if you think about it, wouldn't it mean that you need to learn some basic things about function words, or like basic verbs like I am, or like their reordering? Probably yes, right? So you'll be able, even just from the Bible, you'll be able to learn like very basic things. And you can use that to synthesize more data in the more modern data, like the modern, like university, like modern sentences that you might have. And then you can use then your synthesized data in another iteration to do better.
Okay, thank you.
Yeah. Leon, you had a question too?
Oh, I'm sorry. I forgot to unraise my hand.
Oh, okay. Cool. All right. So let me go forward. What else do I have? Oh yeah. So this is the end of my slides, and I wanted to actually go through a tutorial with y'all. So let me go through very briefly through the current research directions in neural machine translation. So one is, so far, like, all we have done is we have trained models to translate from one sequence into another sequence, right? And the fact is that you can use the exact same model to go from like an audio sequence to a word sequence, from a character sequence. Like, you can think of like a task that is at the character level, right? Like transliteration, like grapheme to phoneme conversion, from orthography to IPA that David talked about, right? This is a sequence to sequence task that you can do with these types of models, where you put your input, most probably the best thing to do is put it at the character level. Now, because morphologically rich languages pose an issue because they have a really large vocabulary, and that's a problem that we kind of solve with using subwords, which hopefully capture segmentations that map to morphemes, which is what David talked about. And then one super interesting approach that can be very useful for especially translating between related languages, or if you have related languages that are more high resource than low resource, is to train multilingual models. So the idea here is, let's say, so Ayodele, are Yoruba and Igbo related?
Yeah, they are somewhat related. Yeah, they are the closest tribe to in the country.
So let's say we have some Igbo English parallel data, but for some reason we have a lot more Yoruba to English parallel data, and we know that Igbo and Yoruba are related. Then we can try to train a model that goes from both of them into English, or the opposite. And in order to leverage the similarities between Yoruba and Igbo, for example. And for instance, Leon, I have trained inflection systems for Aramaic, like for Syriac, that used data from Arabic and from Hebrew, which are related languages. And you can do a lot better by using the related language data, because there are similar phenomena that happen in both languages, and your model can actually learn to generalize across those. So for example, there was this work that basically trained a single system to translate between any 100 languages and English, or from English to 100 languages. You might have seen some other papers or like PR announcements that say that automatic machine translation has achieved human parity in some sense, which means that our automatic models can do as well as a human translator. This is not true. It might be somewhat true for extremely very high resource pairs like Chinese to English, and according to some metric, like if you only focus at the sentence level. But at the same time, what we really need is document level translation, right? So if you think about it, sentences are almost always never like just on their own. And within documents, you also have things like now for a resolution, right? So you say something like, oh, I was on my phone. And then in the next sentence, you will say, oh, yes, I was on my phone. Next sentence, I put it down after I finished my call. So what is it in the second sentence, right? It refers to the phone, which is the information in the previous sentence. So that's why we actually need document level translation eventually, if we have enough data. And then the last thing has to do with domain adaptation, which is the thing that Ayodele touched, which is if I have parallel data and I train on a single domain, like the Bible, or in the case of European languages, we have a lot of parallel data from the European Parliament proceedings. Can I use this to translate like tweets or something from Reddit, or a news article, or a scientific article from like for a medical publication? And the answer is that there's ways to do that. And last, we want models that are actually robust to noise and to perhaps little errors that people make. So when I speak, for example, English, since it's not my native language, I might be making short, like small grammatical mistakes or big grammatical mistakes that do not, you are all able to understand me, but a machine translation system might struggle with because it has only been trained on clean data. So when you give it as an input noisy data, then it doesn't know what to do with it. And that's what we mean by robustness. Yeah, so that's the end of my slides. So, and the end of our time, but I wanted to go through a toolkit called Join NMT. So how about, is it fine with you if I just show you what I wanted to do? And what we're gonna do is, I'm gonna have you follow a tutorial at your own pace, like today, tomorrow, or something like that. And we can touch base like on Friday or by like next week if you want to work on machine translation to make sure that you can actually run those things.